And so this is still the last part here of part C. Where am I here? Actually, for part B, and I was calculating the value of f at 4, and I had it down right to here. So I'm going to move this on over where I had 5 plus, and again, I'm showing this the very longest row possible. I'm trying to break it up into a lot of workable pieces. I know some of you guys did the anti-differentiation way up here and went from there. I split it up into pieces. So I had my 5 plus 5 times the integral. I pulled that constant out front, e to the negative x over 3. I did the derivative, the antiderivative of 3, which was 3x. I evaluated it from 0 to 4, and I ended up with a minus 12. So when I clean that up, and these aren't all necessary steps to show. This was given 3 points, and let me tell you what they were for. There was one for setting up the original integral, one for the antiderivative, which could have been considered here, or I'm actually still in the process of finding it, and then also one for the final answer. But if you went right from your integral to your antiderivative, that's just fine. I'm just showing every step. So on here I've got the integral x over 3 dx. This is technically a u substitution problem. There's, we've had so many of them like this that, you let u equal your negative x over 3, your du would be negative 1/3, you get negative 3. We've had those a lot, so you can work that out yourself, but what you end up getting is a negative 3, which is going to make a minus 15, and then you get your e to the u, which would be e to the negative x over 3. And again, my negative 7 came from combining those two constants. And I am evaluating that thing from 0 to 4. And then you guys can continue with the rest of that. It's pretty straightforward. The final answer on that one, you actually end up adding 15 to that negative 7. You end up with 8 minus 15e to the negative 4/3 if you do your integrating correctly. All right, so let's take a look at the next one. For part C, I'm trying to figure out on the interval where I have an absolute maximum. This is kind of important that I realize that it says absolute because I need to also consider the endpoints. So let's go take a look up here at the graph of where an absolute maximum might occur for f. And remember, a maximum will occur where the derivative is 0, and then where it also goes from positive to negative. So here's my candidate right here. And again, this is called a candidate analysis when I'm considering this, and then also the endpoints. It's not necessary really to evaluate it at negative 4 and 4 for this one, and let me show you why when you have a graph like that. But first of all, they gave me what that x value was there. So first of all, under consideration, I would say there's a relative, for sure, maximum right here. So I'm going to write this, relative max at x equals 3 times the natural log of 5/3, and I should justify why. And I'll say since, and again, I've got 2 reasons for that. I can say because f prime of x, don't say it, no pronouns allowed, goes or changes, would be a better word, from positive to negative. Don't just say it's the 0, actually. So again, when we're doing these problems that involve graphs, we do more using words like changes from positive to negative, or I could say because f itself goes from increasing to decreasing, but because this is a graph of f prime, this is the most logic reason right there. Now, also under consideration are what happens at the endpoints, but keep in mind I am looking for the absolute max of f, and what f is basically the integral of f prime, so I'm kind of looking at what's happening with the area under the curve here. Well, you'll notice that this, because f prime is positive in this whole region, f was increasing. So f increased from negative 4 all the way, and I'm going to use a different color. You might say, well, this graph isn't increasing. Well, this is f prime, and the fact that it's above the x-axis means that it was increasing. It was actually 0 there temporarily, but it still continued increasing. It's still increasing, just less dramatically. And it increases all the way on up to 3 ln 5/3, and then it starts to decrease. So a suitable reasoning for why this is must be absolute would just be this. Must be absolute you don't have to actually evaluate f of -4 and f of 4, which you'd actually done over here. That's called the candidate test. You can actually just use graphical analysis and say it must be absolute max since f increases from, and you don't have to explain why. I mean, I know it increases because the derivative is positive in this whole section, but you can just say since f increases from -4, and you could use bracket notation, but I'm going to just say from -4 to 3 ln 5/3, and then decreases for the rest of the interval. And I'm not going to write the rest of that out. And I know it decreases because the derivative is negative here. Alright, so the last one is the one that was the wild card. And most of you did quite well on this one. I picked one that was actually, this was off the practice exam that you did the multiple choice for. So that's where I got this question from. It wasn't a specific year, it was the College Board, what they released as a practice exam. So again, let's take a look at what we've got here. It's always good. This is a graph of f. And again, most of, if not all of my questions are about g, g prime, g, g, and g. So I really need to go look at what the function g is doing. G is accumulating the area under the curve from 1 to x. So if I'm just asked for g of 1, and almost everybody got these two correct, it was very consistent, but when I integrate from 1 to 1, I get 0. And my derivative is just saying, well, what's the derivative at 1? But again, we've got our second fundamental theorem of calculus that says g prime of x is simply equal to f of x, which would be f of 1, which is also equal to 0. So that was 2 points, one for each of those being 0. The next asks me when g is increasing. Well, I need to stop. G is increasing, let's write this, where g prime of x is greater than 0. Well, g prime of x is actually f of x. So let's go do that. You might say, how do you know that? Well, because when we take the derivative, the second fundamental theorem of calculus says that we are allowed to simply dump this in. And we've proved it multiple times. You need to recognize it and dump that in there. So this is really the graph of the derivative of g. So when I want to know when it's increasing, I really just want to know where this graph, where it's positive. Well, that's where it falls above the x-axis. Some of you said that was from 1 to 3. Go back to the original graph. This is the graph of the sine function, which is 0 at pi is when this is going to hit. It's actually ln x times sine x, but at sine pi I would get 0. This is pi over here, it's not 3. So the best answer for that is very succinct. You would just say it's increasing on 1 pi, and then your reasoning can just be because g prime of x is greater than 0. It can be as simple as that for that one. Let me extend the page a little bit here. And then and that was 4 points. It was 2 for each one of those. So 2 points for this, 2 points for this. The next one is a little tricky because again I've got this absolute minimum. So I do need to know, there's several points that are given for this, and they give you 3 when I was looking at the point specs. And what they do is they need to have you make sure that you know what to consider. So I have a minimum. Let's write this, a minimum where the derivative of g changes, and don't give me all of them where it changes sign. If it says a minimum, I just need it to change from negative. Some of you are considering every possible critical point, but if it just says minimum, then we look for where it's going from negative to positive. If it just says max, I want to know where it goes from positive to negative. I don't need to list all critical points, just any that would supply me with a minimum. So I have a minimum where g prime changes from negative to positive. Okay? So let's go take a look at where that happens. Where do we change from negative to positive on that interval? Well, I need to go back to my graph and look at that. I'm not looking at the graph. So you can obviously see this is the graph of the derivative, and here it's negative, 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 0, positive, which means the original graph must have achieved a minimum right here. The rest of this, it never does that again. There's a maximum candidate, but no others. So on that one, I would say by is writing that minimum where g prime of x changes from negative to positive, and then you could say which occurs, it's very common, which occurs at x equals 1. All right? But keep in mind, when you're doing absolute, you have to keep in mind that you have to include the endpoints as long as it's close. I may very well have a minimum at 2 pi, and it also needs to be considered. We also must consider 2 pi, and really all I have to do is see if the 2 pi will provide me with something that's less than what I get when I do 1. So really what I'm trying to do is figure out, and again, what happens here at 2 pi with my function g. Well, g is the area under the curve, all right? So I know that at 1, g reached a relative minimum for sure. But watch my reasoning for why 2 pi is actually the absolute minimum. The function g is collecting the area under the curve from 1. So watch, right here, I'm starting at 1. I'm collecting area, collecting area, collecting area, collecting area, collecting area. Right here is where it's got its maximum. And then I start to go negative, 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 negative. You can see that the negative area is much greater, that's kind of bad, in absolute value, than the positive area. So when I hit 2 pi, it's going to be negative. You don't have to explain all that. You can just say g of 2 pi is less than 0. You don't have to, you could again say because I'm accumulating area, there's more of it under than over. You could give some sort of an explanation with less thans and greater thans, but really if you just say that g of 2 pi is less than 0 and g of 1 equaled 0. How do I know that? We did it back up here. It integrates from 1 to 1 and 0. So since g of 2 pi is negative and g of 1 is 0, actually 2 pi, I should say x equals 2 pi, is the absolute maximum. All right, so that was worth 3 points. And they didn't say how to assign the 3 points. So I think there was one for identifying this as a candidate and explaining why. So if you did that, I actually gave you 2 C's by yours, which means I gave you 2 points. Some of you just said that 2 pi was a minimum without kind of explaining why it took precedence or was your answer above and beyond an answer of x equals 1. So for part D, all right, last one up, and I've got, hopefully I can do this in 2 minutes or less. I want to know, is there a value of x where the graph of g is tangent to the x-axis? Well, 2 things happen when you're tangent to the x-axis. First of all, your derivative is equal to 0, and also your value there is equal to 0. So really what I'm looking for is there a place where the derivative is equal to 0 and g of x is equal to 0? So when I go back up here, I've got 2 things up for consideration. This one has a derivative of 0, this has a derivative of 0, and this has a derivative of 0. Some of you told me that all 3 of those were answers, but that only is where I have a derivative of 0, which means, it could have been like this, could have been like that. I want to make sure it also hit the x-axis, because that's what it means to be tangent, is that you make it once like this. So I want to know not only where's the derivative equal to 0, here's my 3 up for consideration, but at any of those, is the value of g also 0? Well, it's not here and it's not here. Again, g is collecting the area under the curve, and from 1 to 1, we already said g of 0 is 0. So again, you don't need all those words. This will suffice for a decent answer for your 2 points for part D. You can say yes, at x equals 1. And then for your justification, you can just say because, or since, or whatever connector you want there, since the derivative at x is equal to the value at x, and they're both equal to 0. That's a very good reason for why I have a tangent to the x-axis there. I've got a derivative equal to 0, and I've got the value equals 0. And the only way that can happen is if I nick it or if I nick it. And it means that that provides me a tangent to the x-axis. And I am done with exactly 4 seconds to spare. So you guys have a great day.